Another one bites the dust. Howdy, the bite. Unexpected geological activity on dwarf planet CERES shocks scientists. It's not supposed to do that. Surprise! Geoscientists at Virginia Tech may have figured out why CERES, a dwarf planet and the largest celestial body in the solar system asteroid belt, was found to show unexpected geological activity, according to a recent press release. In fact, what's going on? In fact, their findings, as detailed in a paper published in the journal Advances earlier this year, might just change the way that we think about dwarf planets altogether. Hot potato. Scientists have known of CERES' existence for quite a while, though it wasn't until 2015 that NASA's Dawn probe gave researchers a closer look at the rocky body. To their surprise, scientists discovered CERES to have interesting geological features such as plateaus, mineral deposits, and surface fractures, all signs that CERES once supported seismic activity and even an ocean. To confirm that theory, however, the dwarf would have needed a way to generate heat at some point in its history, something scientists believe smaller planetary bodies to be incapable of. Radioactive, mostly due to the wild way they form. Larger planets like our own start out as hot, triggering powering geological activity, and cool down over time. CERES, on the other hand, was never big enough to be a true planet and thus couldn't have generated heat during formation. But according to the scientists' computer modeling of CERES' distant past, the dwarf planet didn't have to start hot in order to generate heat. So I just wonder how they were modeling CERES' distant past. Rather, they believe that the dwarf, which scientists believe contained radioactive elements uranium and thorium, actually became heated due to interior radioactive decay, which fascinatingly took the body from cold to cold once again, as opposed to the hot to cold pattern traditionally seen in larger planets. Yeah. What we've shown in this paper is that the radiogenic heating all on its own is enough to create interesting geology. Scott King, a Virginia Tech professor of geosciences, said in a press release, "Hopefully this model will be able to provide some insight into the other dwarf planets and even some moons came to be." In any case, it serves as a fascinating reminder of how little we really know about our cosmos formed and how much there is left to discover. Where is the press release? Recent press release. I checked out the paper a bit. Not now. Phys.org modeling reveals how dwarf planet CERES powers unexpected geological activity. This illustration models the topography in meters of CERES from NASA's Dawn project, with some of the dwarf planet's major craters being labeled. The black lines represent the faults described by Scott King's paper. Credit Scott King. Alright. For a long time, our view of CERES was fuzzy, said Scott King, a geoscientist in the Virginia Tech College of Science. A dwarf planet and the largest body found in the asteroid belt, the region between Jupiter and Mars, speckled with hundreds of thousands of asteroids. Yeah, because there are many craters. That's why they think there are thousands of asteroids. CERES had no distinguishable surface features in existing telescopic observations from Earth. Then, in 2015, the hazy orb that was CERES came into view. That view was stunning to scientists such as King. Data and images collected by NASA's Dawn mission gave a clearer picture of the surface, including its composition and structure, which revealed unexpected geologic activity. Scientists had seen the general size of CERES in early observations. It was so small, it was assumed to be inactive. Instead, Dawn discovered a large plateau on one side of CERES that covered a fraction of the dwarf planet, similar to what a continent might take up on Earth. Surrounding it were fractures in rocks clustered in one location. And there were visible traces of an ocean world, deposits all over the surface where minerals had condensed as water evaporated. The mark of a freezing ocean. A professor in the Department of Geosciences, King, who mostly studies larger bodies such as planets, wanted to know how a body as small as CERES could generate the heat needed to power that kind of geological activity and account for the surface features picked up by Dawn. Through modeling, he and a team of scientists from multiple universities, as well as the United States Geological Survey and the Planetary Science Institute, found that the decay of radioactive elements within CERES' interior could keep it active. King's studies of big planets such as Earth, Venus, and Mars had always shown him that planets start out hot. The collision between objects that form a planet creates the initial heat. The collision between objects that form a planet creates the initial heat. So it's impossible, if you are in space and you only lose gravitational force, that anything would accumulate bigger than a fist. Like just by gravitational forces. CERES, by contrast, never got big enough to become a planet and generate the heat the same way. To learn how it could still generate enough heat to power geologic activity, he used theories and computational tools previously applied to bigger planets to study CERES' interior, and he looked for evidence that could support his model in data returned by Dawn mission. The team's model of the dwarf's planet interior showed a unique sequence. CERES started out cold and heated up because of the decay of radioactive elements, such as uranium and thorium, which was alone enough to power its activity, until the interior became unstable. What I would see in the model is, all of a sudden, one part of the interior would start heating up and would be moving upward, then the other part would be moving downward. All of a sudden, just does it. That instability could explain some of the surface features that had formed on CERES, as revealed by the Dawn mission. The large plateau had formed on only one side of CERES, with nothing on the other side. And the fractures were clustered in a single location around it. The concentration of features in one hemisphere signaled to King that instability had occurred and had left a visible impact. It turned out that you could show in the model that where one hemisphere had this instability that was rising up, it would cause extension at the surface, and it was consistent with these patterns of fractures. Based on the team's model, CERES didn't follow a planet's typical pattern of hot first and cool second, with its own pattern of cool, hot, and cool again, What we have shown in this paper is that radiogenic heating all on its own is enough to create interesting geologic. He sees similarities to CERES in the moons of Uranus, which a study commissioned by NASA and the National Science Foundation recently deemed high priority for a major robotic mission, with additional improvements to the model. He looks forward to exploring their interiors as well. Some of the moons are not too different in size for CERES, King said. I think applying the model would be really exciting. So, we are at ISVA, NASA, watching CME tracker. This yellow ball here, that's Earth. I just noticed that that's not in a straight line at the moment. Whatever that means, seems to be interesting. But anyway, if we go up here, we don't find anything what I tried to tell you. Here we have it. IMF, interplanetary magnetic field lines. And you can see, like if you watch, for example, Stereo B, which is this, as well as Earth and all the others. This is obviously moving towards the sun. What is the green one? Solar Parker probe. Yeah, it's Parker. So they are up to something. They are going closer to the sun. But what I want to point out is these lines. Interplanetary magnetic field lines. And we are at NASA. Here we have NASA. See? And we have the interplanetary magnetic field lines. This means that all of the planetary bodies are connected to the sun. And of course, there are more bodies in our solar system than just in this picture. So each of one is connected to the sun by the interplanetary magnetic field lines. And if we go to null school, watching winds, and then we go to the highest, what we can get here, highest part of the atmosphere, and that's the northern pole, and that's spinning. We go to the southern pole. This is spinning as well. And if we put it like this way and zoom out a little bit more, here would be the sun. Just imagine, let's draw a yellow sun. If we can, that's the sun. And this is our connection to the sun, which is always there, constantaneous, always. The interplanetary magnetic field line, the Birkeland currents, which go through our planet, which go through the sun, our solar system is connected to the center of our galaxy. It's scalable. So the energy which is provided to our Earth, to the sun, to CERES, and all the other planetary bodies is coming this way. And it's going both ways all the time. And I think it's still possible that in Earth's interior we have something like a plasmoid. This is a picture once I created. Deepest quake ever recorded, 987 kilometers. But there is still after that left 5,877.5 kilometers approximately to the center. And as Walt Thornhill explained, with the repellent core, you can imagine something like a geoid, just alive. And here we have some lab plasma, which is reaching to the surface. And where it breaks through, we get Icelandic eruptions and such things. Tongas, La Palmas, volcanoes. So this is how I think, like, those planetary bodies, like CERES or whatever, if they still are active, having earthquakes or whatever, it's the energy which goes through the hole. Which keeps Earth alive and thus keeps us alive. And if there's any fluctuations in this energy stream, we will notice it. There will be strange weather, abnormal anomalies, or what was the other thing? Yesterday they were talking about this warm blob in the oceans. And fluctuations in this energy stream will leave marks which will influence the weather. To the degree of its potential. Until next time, when there is another big pulse coming from the sun and Earth gets charged again. And there will be new marks made. Some are visible with the naked eye, like mountains, rivers, and all these kind of things. And some are just measurable with special tools. That's from the sun. You can even see in this picture how it has a filamentary structure. And just imagine if here would be, for example, Campi Flegrei or Vesuvio, and here Lager Lake in Germany. And here in the middle, we would have the Alps. The ground-to-ground discharge on Earth could have created the Alps in a rather short amount of time. 20 minutes, done. Then you just have to wait until the dust settles and you can build settlements there and be happy about the water which is provided from the mountains. Thanks.